Thank you for the introduction, Greg. And thank you so much for everyone who's coming. Just looking at the numbers, I'm genuinely humbled by how many people are here. I am experiencing some allergies going on, so if you hear me kind of cough or something or drink more water than normal, I just don't want to be coughing the whole time. The one other thing is I recommend if you're on a laptop, making that little zoom with all the people, making it into one small window and placing it at the top right-hand corner here. I've designed this PowerPoint, so hopefully that won't cover up too much stuff right there. So with that, we'll begin. So the roadmap of my talk today follows really the layout of my thesis. First, a quick introduction to wetland ecology and restoration theory, and then the second and third chapters are my actual research projects themselves. But first, I just want to get us all on the same footing on what are wetlands and how are we restoring them. So before we really jump into things, I just want to ask a few existential questions, like what are wetlands and why do we even want to restore them? Well, first, wetlands are just simply areas which get flooded enough to cause the development of special soils and uniquely adapted vegetation. Wetlands can span a lot of different ecosystems and their frequency of flooding, such as prairie potholes every 1 to 3 years in the Midwest, to salt marshes getting flooded twice a day by the tides in New England. The vegetation can look very different from water lilies of shallow ponds to red maples and cypresses of woody swamps. So when we talk about wetlands, what we're really talking about is a wide range of ecosystems with a few common denominators of hydrology, wetland soils, and aquatic vegetation. Additionally, wetlands provide more ecosystem services per acre than any other ecosystem on the planet. Wetlands act as a sponge on the landscape by retaining floodwaters. The organic and peaty wetland soils can store carbon, which is helpful to combat climate change. Wetland soils are perfect sites to alleviate the overapplication of nitrogen through denitrification. It's been estimated that over 5,000 plants and at least 1/3 of all bird species in the United States are dependent on wetlands for at least part of their life cycle. And a recent estimate of global ecosystem services of both freshwater and tidal wetlands put all of these services in today's dollars at roughly twice the total expenditure of the entire US government in 2019. So we're not talking about little ponds here, we're talking about things that actually serve us as human beings on a regular basis. However, wetlands were not really viewed with the same enthusiasm as me. Throughout most of our history, wetlands were viewed really as obstacles to progress. And since the founding of our country, we've really lost almost 50% of all wetlands that used to exist on the landscape in the conterminous United States, with heavy losses you can see in the right-hand map of the Midwest, California, and the Mississippi floodplain. An entire mass of swamps and marshes that used to dominate landscapes are barely fractions of their former selves, including the Mississippi bottomland, the San Francisco salt marshes, and the Black Swamp in Ohio. However, societies and federal government's view of wetlands shifted dramatically with the Clean Water Act of 1972. From funding and actively encouraging wetland destruction, the federal government and many states took on the role of conservation and protection through active restoration and the Section 404 permit program. So under the Section 404 permit program, third parties are now required to mitigate the destruction of wetlands by either actively creating or restoring wetlands somewhere else to compensate the public. That's us. So wetland mitigation, as it came to be called, became huge business by the 2000s. In just 2004 to 2009, enough uplands were transformed to wetlands in the United States to cover all of Rockingham County in New Hampshire. It would be like all of that shaded blue was just one giant wetland. And so one of the jobs of government regulators is to ensure that these replacement wetlands are ecologically successful, that we as the public are still getting those valuable ecosystem services and we're sustaining biodiversity before damaging these wetlands. So over time, restoration ecology has found that one of the biggest ways to ensure success is through consistent monitoring and evaluation of these projects. And there's two really, really cool models, at least I think they're really cool, that have come out of wetland restoration and have really yielded some interesting ways to evaluate the recovery of wetlands. And to illustrate what these kind of models look like, I just want to walk through a quick fun example. So let's say some random company, I don't know, let's say Delta Airlines decided to build a new hangar outside of Pease Traceport, just south of the Great Bay National Wildlife Refuge. And they went to New Hampshire regulators from the Department of Environmental Services and allowed for a swamp to be destroyed just south of the wildlife refuge. In exchange for them to destroy the swamp, they required Delta to construct a new wetland down in Greenland. And let's say as burgeoning ecologists, we decide to monitor this wetland over time to see how it changes. And so let's say maybe after a few years, it becomes a shallow pond full of white water lilies. Maybe after 5 years, it becomes a cattail marsh. And finally, after 20 years, it finally starts to resemble that woody swamp that we saw that Delta destroyed. And let's just say maybe throughout this time, we were actually monitoring the plant biomass, and the biomass increased over time. You know, went from water lilies to herbaceous cattails to woody trees. So the first model we can apply is this restoration trajectory analysis. When we apply this analysis, what we're really asking ourselves is, can I make a general prediction of how long it takes a certain metric to recover? So in this example, we're looking at how long does it take for plant biomass to reach these original swamp levels? And essentially what we're doing is applying a linear or nonlinear regression over time in order to generalize that recovery, or in this case, the buildup of the plant mass by the time it reaches original swamp levels. The second model is this progression deviation model, which was developed by Matthews and Indris 2010. The model is simply a qualitative way to think about how our wetland has changed over time, where let's say each ecosystem occupies some two-dimensional space. It's abstract. This is simply a framework of thinking about long-term changes over time. So when we employ the model, we ask ourselves, is the restoration moving closer or further away from our desired community? And for all those statistically inclined, this is very similar to non-metric multidimensional scaling, just in a purely qualitative way. So you're probably wondering by now, like, what the heck is Grant's thesis even about? Like wetland history, wetland ecology, these weird models. Well, over the past 3 years, what I ended up doing is applying these two models and other modern restoration theory to two really cool and unique wetland case studies in New Hampshire. The first one, my second chapter, it applies a restoration trajectory on restored salt marshes within the first 5 years after construction. The second one, I applied the progression deviation model to better understand how a freshwater wetland shifted over a 35-year time period. And with that, you know, getting some kind of baseline knowledge, we can now jump in and better understand these research projects. And the first one I'm going to start with, which I know most of you are more familiar with, is my living shoreline or my salt marsh work. So it's well known that coastal habitats face just an uncertain future from a variety of stressors. Salt marshes in the Gulf of Maine and in the Great Bay system of New Hampshire are no exception to the nationwide trend. Salt marshes can actively erode or just simply collapse as a result of sea level rise, increased frequency of intense coastal storms, and increased salinity stress from drought. And as salt marshes erode and collapse, the immediate upland property, such as roads, homes, infrastructure, they become increasingly threatened with erosion and flooding themselves. So from a broad perspective, coastal communities generally have 3 tools to address shoreline erosion. First, in the top right-hand corner, they could just do nothing and hope those stressors are ameliorated and maybe the salt marsh comes back, which is a very low chance. Second, they could harden the shorelines by constructing concrete seawalls or riprap armoring, but those structures lose resiliency over time and they usually fail in high-intensity storms. Lastly, coastal communities can invest in nature-based shoreline stabilization methods, which is really just a fancy word of restoring coastal habitats. And what we've been generally calling that are called living shorelines. So living shorelines is the combination of both traditional shoreline engineering, such as seawalls or riprap armoring, and the ecological restoration of coastal habitats. And one of the most common techniques is the creation or restoration of salt marshes and protective coves, and the construction of a 3 to 4 foot riprap seal at the seaward edge. And this riprap seal is essentially just small boulders and tree stumps that makes just a very small wall. The riprap seal initially reduces wave energy and provides time for vegetation to root out and stabilize the soil. Then as the salt marsh system recovers over time, the resilience of that shoreline should increase and hopefully gain sediment and elevation. And one example of a living shoreline, which I've shown below, is the one at Wagon Hill Farm in Durham, New Hampshire, which probably many of you have been to or not realized was there. You know, that existing shore salt marsh eroded over a decade with erosion rates estimated at almost half a foot a year. And so this living shoreline was put into place to protect the dog park and enhance the salt marsh habitat within the Great Bay system. So from a general overview standpoint, the construction of living shorelines is fairly straightforward. First, the site is regraded with the addition of sandy fill material for the correct tidal elevations. Second, we construct this riprap seal out of small boulders or stumps. And lastly, we're going to come in and plant the salt marsh vegetation at the correct height. You know, we're going to use things like smooth cordgrass, salt marsh hay, and spike grass. And hopefully afterwards, we're going to monitor and evaluate this to make sure this project is functioning correctly. And that's where my research comes into place. But you might be asking yourselves, well, this all seems really cool, Graham, but like, why are we talking about like living shorelines in New Hampshire? Well, over the past 5 to 6 years, the New Hampshire Department of Environmental Services have been steadily shifting their focus to living shorelines as the regulatory preferred shoreline stabilization method. And they've taken many actions in the past 5 years to do that. They've developed planning tools to locate adequate locations for future living shorelines. In 2019, they just totally changed the tidal shoreline stabilization permit, which gave preference to living shorelines. And additionally, the state has directed funding into 3 pilot projects since 2016 in the Great Bay system. So we're trying to move in that direction, but we don't know what these projects will look like. And one of the problems with that is, despite this growing emphasis on living shorelines throughout the country, it's still a relatively new science with only a handful of published studies and reports on their efficacy and performance. Additionally, almost all of these studies and reports have been located in the Chesapeake Bay and on the North Carolina coast seen on that map. You notice they're all below the Mason-Dixon line. So this lack of knowledge on the performance of living shorelines may leave researchers and regulators really flying blind in terms of their expectation and maintenance needs, especially when you consider that northern New England experiences different climatic conditions than the Chesapeake Bay, including shorter growing seasons and the reality of ice rafting during the winter. So I set out an overarching research goal of improving the design, expectation, and maintenance of future projects by completing 2 objectives. First, I quantified the short-term recovery of 3 living shorelines in New Hampshire. And second, I documented all of the possible maintenance needs that stakeholders will need to plan for in their budget and initial planning stages. And so first, we're going to look at how I quantified the recovery of these systems. So like I said, there's 3 pilot projects that were constructed in New Hampshire in the past 5 years. The first was North Mill Pond in Portsmouth, the second Cuts Cove in Portsmouth, and the third Wagon Hill Farm in Durham. And to quantify the recovery of these salt marsh systems, we designed a modified before-after control impact study, which is super common in restoration ecology, where each living shoreline was paired with a reference salt marsh, which is like what we want our salt marshes to be, and then also a degraded shoreline or an armored shoreline, which is what would that shoreline look like if we had done no restoration on it. And so to gauge the restoration performance, we monitored 3 aspects of the salt marsh system. We looked at vegetation, we looked at fauna, and we looked at biogeochemical processes. And so for vegetation, we conducted plot sampling at all these sites and looked at the visual cover and species richness. For fauna, we conducted 1 round of minnow trapping at each site to monitor mummichug densities and adult length. And for biogeochemical processes, we collected pore water at each of the vegetation plots for salinity, redox potential, pH, and sulfides. All sampling was conducted in August and September of 2019 and 2020, and minnow trapping took place in only 2020. And of course, during COVID, for safety stuff, we donned the mask and we got out there anyway. So to quantify the recovery of these living shorelines, I used this thing called the Restoration Performance Index, which was created by my advisor who you heard earlier, Greg Moore. The RPI is simply an evaluation tool that measures both the progress achieved based on the degraded shoreline, so how much salt marsh have we possibly created, and the progress that remains to reach our reference shoreline, so reach our restoration goals. The RPI simply gives a score from 0 to 1, where 1 really means that we've reached all of our goals, and 0 means that our restoration efforts basically did nothing. And so then I applied a restoration trajectory analysis to these RPI scores over the age of the project, which spans 0 to 4 years. I applied a 3-parameter logistic equation based off just the shape of the data. Additionally, I analyzed the recovery of the metrics where a trajectory could not be conducted. And to do that, I simply conducted student t-test comparisons for individual metrics for the 2020 data. So what did I find out there after doing this for 2 years and looking at a bunch of different sites? Well, after 2 years of monitoring, the RPI displayed a pattern of rapid recovery of the salt marsh systems, which was primarily driven by the vegetation and the fish community. I will note here on this figure, years 0 and 3 did not have any fish sampling in it because they were only taken in 2019. So the biogeochemical processes also continued to lag in the recovery as vegetation and nectin reached high scores. From the RPI, the living shorelines recovered a little over 50% of ecosystem structure, function, and services within about 4 years. I mean, for me, I think that's kind of incredible that, within 4 years, we have created really sustaining salt marshes. Yes, they might not meet our goals, but that's still 50% of the structure and function and services that simply were not there before we took action. On the right, we had a pretty well-fit 3-parameter logistic regression, which really solidified the trends we see with the bar graphs. And this regression identified both a phase of rapid recovery within the first 2 years, and then really a plateau of recovery. Maybe the recovery stalling, or it's entered a phase of maybe incremental progress. When diving deeper into the RPI, or especially with the unweighted vegetation community, which was just composed of visual cover and species richness, it followed really the same similar trajectory. And again, it identified within 2 years a rapid recovery, and then a slowing down of that recovery, or even a plateau. And then when we compared just the visual cover in 2020, we found that visual cover reached statistical significance, or statistical equivalence with the reference marsh by year 4. So what that really means is after 4 years of constructing these salt marshes, the vegetation visual cover, or really, if you want to think about the abundance of vegetation, is equivalent to our reference marshes in just 4 years. When diving deeper into the response of the mummichugs, so those little fish we kept catching in our traps, we found an extremely quick recovery as well. It seems that mummichugs responded quickly to this presence of salt marsh habitat and immediately began utilizing the space. One thing I do want to point is that Wagon Hill Farm, after just 1 year, had statistically greater catch rate of mummichugs than our reference salt marsh. And that was just after 1 year. However, the soils of these living shorelines remain highly aerobic, or they remain really oxygenated compared to anaerobic, or really soils without any oxygen that are really saturated from the tides. And part of that could be because when we build these living shorelines, they're made with sandy fill, which allows for the tides to quickly drain out. This cycle of flooding and drainage might require that wetland soils take much longer time to recover than vegetation or fish. And so taking a break for a second, the second part of this project, I was really interested in documenting the maintenance needs for these projects. Just because we build these projects doesn't mean that they're automatically successful and we can walk away. There's normally some kind of maintenance needs they need for at least the first 5 years. So I ended up compiling 3 maintenance needs. The first one was that we witnessed intense geese herbivory from October to December, which really damaged the Cuts Cove living shoreline in both 2019 and 2020. Now, geese are known to eat rhizomes and the roots of spartina grass in the low marsh. That's totally normal. That's well documented. However, going back to the fact that we use really sandy materials in this, the geese basically could rip out entire plants with ease. And so they basically had a buffet waiting for them when they migrated through. What happened is, if you look in the middle picture, basically Cuts Cove, a portion of it just looked like a landmine, or a minefield had gone off. so this site will require additional plantings. The second issue we identified while monitoring was a high mortality of Spartina plugs within the first few meters of the seaward edge. The trends were quite noticeable at North Mill Pond and Cuts Cove. And at North Mill Pond, close to 50% of that originally planted low marsh was just completely bare within 4 years, which you can see the outlines of. At Cuts Cove, the first few meters also had very little vegetation. And part of the reason this could be because of higher tidal energy, higher inundation, and maybe just herbivory by intertidal snails, and that could all just contribute to lower vegetation. The third possible issue that living shorelines in New Hampshire might face is high rack deposition that smothers and kills off patches of the vegetation community. At North Mill Pond and a limited degree at Wagano Farm, variable rack deposition did not allow for the full development of the vegetation community in the high marsh. What's really going on is really senescent grass, seagrass, and big chunks of algae are floating around these tides, landing on this vegetation and basically smothering it and just killing it, and the tides aren't taking it away. And so to prevent this vegetation die-off, rack is going to need to be raked up and removed after pulse events, especially like storms or just seasonal deposition. And so the management implications for at least this research project can be broken down into two categories. One, our expectations for how these systems can recover, and two, what maintenance or adaptive management needs are there. For future expectations, practitioners should expect 2 phases of recovery, with the first being a rapid recovery to roughly 50% of ecosystem structure and function, which are primarily driven by vegetation and nectin, and then a slower, more incremental recovery as wetland soils develop. The recovery rates that I witnessed in my living shorelines were supported within the literature itself, so we didn't see anything out of the unusual, which even more supports this 2-phase recovery. Secondly, during the planning phase of these projects, stakeholders should include monitoring and maintenance costs into these budgets. 3 possible maintenance needs for living shorelines will be annual replantings for the first 5 years, proactive keys management, and of course, rack removal to allow vegetation to continue growing. So at the conclusion of this research project, I will say that these living shorelines show incredible promise in both stabilizing eroding shorelines, as well as restoring valuable coastal habitats. And I would hope that these projects continue in the Great Bay because they just show so much progress, especially the fact that within 4 years, 50% of the structure and the function of these salt marshes come back. So I'm going to take a sip of water here for a second, and then we'll jump into my second research project. This next one's going to focus on really one freshwater wetland just over a really long time period. And so for a little background information, typically wetland creation and restoration projects are monitored for 5 years, and then they're left to continue on their recovery. And the assumption is within ecology and within regulation practices that once wetlands are make sure that they've done okay within 5 years, they'll probably continue on their recovery path. However, a few studies that have revisited a number of these wetlands after that 5-year monitoring time have really found either incomplete recoveries or even declines in function and structure. Over to the right in the graph, Marino, Mateus et al. 2012 did a fantastic and heavily cited meta-analysis looking at the fate of restored wetland ecosystems. And what he found was that vegetation, fauna, and wetland soils just never recovered to the restoration goals or the reference levels, even after 50 years. And so as an ecologist, if you're a regulator who's got to permit maybe some wetland destruction and mitigation, this looks kind of scary. And so to improve the design and general expectations of future projects, ecologists have spent a considerable amount of time detailing the development of the vegetation community. And they've essentially been asking for about 30 years now, how does the vegetation community change over time? What can we expect? And so across the country, there's been a lot of research over the past 20 to 30 years, and there seems to be a consensus at least on 3 patterns. And those are with the life history, the species richness, and the rate of succession. And we're going to walk through each of those. So If we look at species richness, or simply just the number of species present in the wetland, there seems to be a really predictable pattern going on. It seems that there's a rapid accumulation of species within the first 5 years as annuals and perennials colonize the newly created wetland. Species richness tends to plateau after 10 to 15 years, depending on who you talk to and which kind of system you're studying. And after 15 years, the species richness will either remain relatively constant or it'll decline as annuals begin being outcompeted by perennials. And if we look at species composition, or simply just the list of all the species known in the wetland, there seems to be a pattern when we look at the proportion of annuals, perennials, and woody species. At first, annuals dominate the community with few perennials and woody species present. Annuals are quick to colonize this new site, and they usually beat out perennials and woody species to the site. So they kind of have an edge for the first 5 years. However, over time, annuals get outcompeted by perennials and woodies, and it seems that perennials just tend to dominate the community after 5 years, except with small increases by woody species. And then when we look at the rate of succession, it's only been documented by just a few studies, but it seems that there's the same pattern going on over and over again. First, it seems that the number of species that the wetland annually gains sees a really quick initial jump and then tapers off quite a bit, which makes sense. If there's no species there, you can get a lot of species to jump into this wetland, and then they've probably taken up all the space. It also makes sense based on what we saw with species richness, a rapid accumulation of species, then a plateau. Next, the number of species the wetland annually loses is zero initially because there are no species to lose. But then after a while, there's a small jump, but then it also tapers off. Over time, if we include both those metrics together in turnover, or what I call the rate of succession, it usually follows the pattern of the species gain line. And another way to view this is to say that the wetland undergoes rapid succession early on and then tapers off to a steady state with really small turnover. It might be losing a species here or there, but really after 15 years, the species composition is really staying relatively the same. And what was so interesting about this was back in 1996, Mitch and Wilson published a paper about where the state of the science was for wetlands. And they made this really passing claim at the end of their paper that basically said, vegetation, communities, and wetlands really mature within 15 to 20 years. And for some reason, there wasn't a lot of data to back this up. And they essentially, it just became dogma. People just picked it up and they just ran with it, even though there wasn't a lot of data to confirm. So I wondered if there was a way to test these theories in the long term, but where could I find a created wetland old enough to verify Mitch and Wilson's claim? Well, my advisor happily introduced me to Quarry Pine on a field trip in his aquatic botany course. And so let's just take a step back. So Quarry Pine is a 10-acre created wetland for mitigation purposes. It's in an old abandoned quarry in Portsmouth, New Hampshire. The wetland was created in 1985 to 1986 through the construction of mounds and pools for hydrologic heterogeneity. The cool thing about this wetland is that they scraped away the top 6 inches of sediment from that original wetland, transported it over to this new wetland, and spread it out evenly. They conducted no plantings and solely relied on the seed bank for the vegetation community, which is super rare. Normally, wetlands get a lot of plantings. And essentially, this created a large wetland in kind of an urban corridor. And so you're probably asking yourself, well, Grant, that's nice that you found an old wetland. Like, that's really cool, but like, how are you going to see that it changed over time? And well, for that, I really have to thank Dr. Garrett Crowe, who was the old herbarium director of UNH and the man who literally wrote the book on wetland botany in New England. Dr. Crowe had the foresight to enlist graduate students to conduct complete floral surveys, in both in 1992, so roughly 7 years after construction, and 2002, 17 years after construction. So in 1992, they compiled every single plant species that existed in that wetland and created a detailed map of the dominant vegetation communities. In 2002, they compiled another floral inventory, and they provided some comments on that original map. And so when I was read through these papers and after going on that field trip, I realized I had a perfect case study to look at this. Like this is really rare to find. And I will say the reason I get so excited about this is after doing the literature review and looking through other studies, this seems to be the oldest, or at least the longest record for like an oldest created wetland. Most of them usually stop at 25 years. There's not really a 35-year-old record here. And yes, it's only 3 points, but it's still 35 years and it's incredibly useful. So in this, I asked kind of 2 research questions about Quarry Pine, especially with this unique long-term data set. First, did the vegetation community of Quarry Pine follow these documented patterns that we just kind of walked through? And second, did the vegetation community remain dynamic after 15 years? Really maybe contrary to what Mitch and Wilson 1996 stated. And so I tackled these 2 research questions from 2 different angles. First, from species composition, and then second, from the distribution of these wetland communities themselves. And so first, I looked at species composition. So I and Natalie White conducted a full floral survey following the methods of the prior 2 studies of Quarry Pine. To do this, Natalie White and I conducted meander surveys, kind of like a lot like the star is going, from mid-May to mid-October in 2020. All species found within the wetland were either identified on site, or really, since a lot of these required dissection, I had to bring it back to my lab, which during COVID time meant my kitchen table and a borrowed microscope. All species were either classified as annuals, perennial, or woody based off the USDA plants database. And then I calculated the rate of succession using 2 different metrics. First, the Sorensen Similarity Index, which is really common in ecology. And then I looked at the annual rate of succession from Anderson 2007, which has been slowly being picked up in restoration ecology itself. And so this is kind of what I found. The way I've structured the next few slides are, I have my results in the left, and then I have, remember, the proposed model in the far right with some notes off to the side. And so when I looked at how species richness changed over time, at first I made the assumption that there were no species present at day 1 of this, which was pretty easy to verify based off the notes from the project. So it seemed like species richness followed similar patterns as the proposed models in the literature, including a rapid increase within the first 10 years, and usually it slowed down. However, if you notice, species richness keeps continuing to increase even after 17 years. And I found that so interesting. So when I dove into what species actually colonized between 2002 and 2020, I found that 70% of the actual gains were actually upland perennial species. And then when I looked at the history of the site, I realized that there was a drastic drought in 2018, and they probably were able to get a foothold then and managed to eke out existence. So if we factor out the upland plants, we find that species richness actually plateaued after 17 years and continued to follow the proposed models that we see in the literature. Next, I looked at the life history of the species composition, and life history followed very similar patterns, with annuals representing about 10% of the community and perennials continuing to dominate the community even after 5 years. I will say the woody vegetation, even though minor, did increase their proportion over time, just like in the model too. Using species composition list, I was able to calculate those 2 forms of the rate of succession. And so first, I kind of want to walk through this graph because it's a little difficult to understand for a second. The y-axis should really read as the percent of the community that changed annually. So it's not the number of species, but it's really a unitless percent of the community itself. Each of these dots is the average annual percent change between each of these 2 time periods, and I kind of made note of them in the graph there. So species gain rates followed the proposed model well, with greater than 20% annual gains for the first 7 years. So again, we see that high colonization. However, we saw a steep drop off after 7 years, and it continued to decrease. The rate of species losses can only be calculated after the 7-year sampling period and was already minimal, with only 1 to 2% of the community lost each year. When we looked at the rate of succession, so the thing we're really, really curious about, it was actually really quite low as well, between 3 to 5% between 1992 and 2020, really. But another way to think about this, and I think it's an easier way to think about this, is just really thinking about how similar is the species composition between each of these sampling periods. And with that, I use the Sorensen Similarity Index. And so what we see between 1992 and 2002, and also 2002 to 2020, about roughly 3/4 of the species persisted that were originally there. And what I found even cooler was, and it was kind of amazed, was that we found 71% of the species found in 1992 had persisted until 2020, which I actually found quite remarkable. And many of those were annuals as well, which we thought we would have gone locally extinct in that site. So altogether, we can answer a few questions. The species composition experienced real dramatic change within the first 7 years after Quarry Pine was constructed. And second, that community, after 5 to 7 years, it remained relatively consistent, reaching a steady state in both the proportion of life history traits, the species richness, and the rates of succession. So overall, it seems that our wetland, even with a longer case study or time frame, it really followed these documented successional patterns. And so next, I want to look at the distribution of wetland vegetation communities. In 2020, I developed a map of the wetland vegetation communities in 3 steps. First, my advisor and the awesome team at the UNH GIS lab flew a drone and captured high resolution imagery of the entire wetland. And by high resolution, I mean 1.67 meters. I could literally be on my computer and look at individual tussock sedges and water lilies. It still blows my mind just to look at this picture. Second, Natalie White and I conducted plot sampling of 104 plots on equally distant transects throughout the wetland. We identified every species in the plot and estimated the visual cover of the ground, the shrub, and the tree layers. So using this information, I was able to classify each plot using the Vegetation Community Manual of New Hampshire. And with that, I was able to classify each plot. And lastly, I used that just wicked awesome aerial imagery in these plots, and I was able to manually draw these wetland communities on our GIS Pro. In order to compare my map, I reclassified Garrett Crow's 1992 map. First, I took his 1992 map of dominant vegetation and reclassified it based off the manual. I then redrew the vegetation communities just using the outlines from the 1992 map. And with both those maps now created and in the right locations, I was able to compare them, calculate areas, and really see the change in areas using the intersect analysis tool. So here I was able to see how cattails grew into open water between 1992 to 2020. Additionally, I was really curious about the quality of the habitat itself. It's nice that we're talking about all these plants, and that's nice, but I was really curious about, what did this actually serve as a great place for fauna? And what we did was we monitored the bird community. So Andy Payne and I conducted 10-minute point count surveys of the bird community every 2 weeks from early June to mid-October to coincide with the breeding and the fall migration season. Each bird species was then classified as either wetland or upland category based off their habitat requirements outlined in Brooks and Cronquist 1990. And so after comparing these 2 maps, I really found 3 major findings. First, there was a large increase in the number of wetland communities from 1992 to 2020. In 1990, there were 4 communities. There was cattail marsh, there was aquatic bed, which are just shallow ponds with floating leaf aquatics. There are tall graminoid meadow marshes, which consist of these tall tussock sedges primarily. And my favorite wetland community is a marshy moat, which is a mudflat area, which really only supports spike sedges or a few other things. However, in 2020, I identified 9 wetland communities based off that manual. And additionally, the marshy moat community no longer existed. So since 1992, there was a gain of 6 new wetland communities. The new wetland communities consisted of scrub shrub cattail marsh, which is really cattail marsh with minor but definite scrub vegetation, mixed tall graminoid scrub shrub marsh, which is just a mouthful to say, and emergent marsh, which is very, very shallow water that allows for different types of emergent vegetation like burr reed and pickerel weed to exist. Additionally, we also saw seasonally flooded red maple swamps. We saw a sedge meadow marsh, a scrub shrub swamp, and we saw a sedge meadow marsh. And then we found that the bird community responded with high species richness and high abundance throughout this wetland. With such a variety of niche space with different wetland communities, many wetland birds and upland birds were able to take advantage of this wetland. Overall, we found 14 wetland species and 25 upland species. And within those wetlands, we actually found 2 secretive marsh bird species, the sora, which is a special concern in New Hampshire, and the Virginia rail. Wetland species consisted of 45% of the total individuals in the wetland. However, 68% of all wetland individuals were just red-winged blackbirds when they basically had a month-long party in June. My second major finding was that those original big 3 communities, cattails, graminoid meadow marshes, and aquatic beds, they changed dramatically since 1992 within themselves. And so I documented that the cattail marsh expanded its local range quite a bit into the aquatic bed here, here, and here. And it expanded its range into the tall graminoid meadow marsh, including places like here, here, and here. Overall, the cattail marsh expanded its original area by over 80%, and subsequently the aquatic bed lost 37% and the meadow marsh 42% of its original area just to the cattails themselves. And then my third major finding was that wetland communities develop at different rates. This might not be a no-brainer, but some people still assume that if you live well into itself, maybe different communities will come at the same pace. And after looking at Quarry Pine, that's just not true, at least in our case study. Looking at the map at 1992, in conjunction with Garrett Crow's comments in 2002, it became clear that 5 communities did not develop until after 17 years, including sedge meadow marsh, red maple swamp, and scrub shrub swamp. If we want to think about it broadly, it really only took 7 years for cattail marsh, aquatic bed, and tall graminoid meadow marsh to develop. And I will say past studies have also confirmed how long it takes for a few of these systems to develop. Out in the prairie pothole region, they've shown that sedge meadow marsh requires 20 years. And there's been a host of papers showing that bottomland hardwood forests also require more than 20 years as well. And I just want to show you what were some of these communities that really developed. And really the big story was woody vegetation came to dominate after 17 years. So just to take a closer look, woody vegetation just spread across the entire wetland and create these new communities. You can see it here with the scrub shrub swamp, here with the cattail scrub shrub marsh, and here with the tall graminoid scrub shrub marsh as well. And now currently the woody vegetation takes up 18% of the entire area, which is up from 0 just 18 years ago. So when I was trying to wrap my head around some of these long-term shifts of community distribution, I use this progression deviation model. Again, this isn't quantitative, this is just qualitative. So if you want to look at this, how I wrap my head around this, in 1986, there was no vegetation. It's really off the graph. In 1992, it seems like the whole wetland was really equally divided between those 3 ecosystems. After another 10 years, cattails expanded their range at the expense of the shallow ponds and the meadow marshes. And then after another 18 years, the rise of woody vegetation on the marsh shifted the community towards more of a woody swamp area with possible declines by the cattail marsh. So overall from Quarry Pine, I feel like I learned 4 important points from this really cool case study. The first one was that species composition really followed these documented patterns in the literature, and it really strengthens them already. The second was, contrary to what Mitch and Wilson in 1996 said, our wetland actually remained highly dynamic after 20 years with the rise of new wetland communities and the expansion of the cattail marsh. Third, with the rise of all these different communities, we also saw high avian diversity in both upland and wetland species. And lastly, which is the big takeaway from this project, which is that long-term repeated case studies are just incredibly useful in understanding the dynamics of restoration projects. Yes, they take a lot of time and money, but they can be incredibly useful. So before I end today, I wanted to end with a few last thoughts about what I think I've learned from this master's, but also just to show off one more plant. First, I think that restoration goals, no matter what system you work in, typically take longer than 5 years of monitoring. And this was shown in both my research projects, and that's shown throughout the literature. And I think it's something that just needs to be repeated again and again. Second, ensuring restoration success sometimes requires intimate knowledge of a site, which sometimes requires the time, the labor, and the money that we don't really give to projects these days. You know, it's really the constraint of the 5-year monitoring period. And lastly, despite maybe setbacks throughout the history of ecological restoration at times, it can be really effective at enhancing ecosystem services and sustaining biodiversity across our landscapes. And it can be really, really useful. So with that, I would just like to take a few seconds, and we're almost done here. Thank you guys so much for being patient and listening through all this. Now, first, I just want to say a huge thanks to my committee who has mentored me this entire time with Greg Moore, David Burdick, and Tom Ballestero. Another huge thanks goes to Natalie White, Angie Payne, Chloe Brownlee, and Chris Peter for all the days in the field, in the lab, and all the mentoring. And of course, I got funded through these projects through UNH, and SER, and New Hampshire Sea Grant. And of course, just because you weren't out in the field, you know, a lot of people helped me along in this journey. You know, for people who listen to my awesome rants about plants, they sent me care packages and random texts of love. They picked up, you know, some truly hard times. And really, we just cheered a lot of beers together. And so for that, I really just want to say thank you just to everyone, even if you weren't out on the marsh with me. And with that, I will take any questions.
Great job, Grant. I will be your MC here for managing the chat, but I encourage people just speak up or, you know, and have Grant field the questions. So let's see what we've got coming in here. We got a quick question, Grant, from Chris. Just a quick note, Chris Wojcicki, I hope I'm saying that right. About chapter 2, birds are generally a good indicator species of ecosystem health, and since so many of them use marshes, it seems like they would have been a good choice for measuring marsh restoration. Why did you choose to quantify mummychug abundance?
Yeah, that's a good question, Chris, especially when you look at comparing my 2 chapters. The first one is that looking at these fringe marshes, birding really isn't the most useful indicator. Birding on salt marshes are really only useful for really big marsh meadows like the Great Marsh, or maybe by the one by Lumberland Creek here in Durham / Newmarket. But on these little fringe marshes, birding really doesn't really get you anywhere. Mummychugs really tell a big difference because they actively look for salt marsh habitat and use it. And also, minnow trapping is just really easy to get some data about the site too. That's a good question.
We got another one here from Aaron. Great job, Grant. How can you take this kind of research and apply it to other areas of the country that have similar ecosystems so we can save these areas and make sure they're closely monitored to thrive for the future?
Yeah, that's a great question, Sis. One of them is just using these fundamental models that over time we've used for restoration, using like restoration trajectory analyses, shifting our focus from yes, no goals to viewing progression over time, like in the RPI. And really, no matter if you just want to think about wetlands, no matter where you go, if you can understand the hydrology, the soils, and the plants, you can probably figure out a lot of what's impacting this from both the stressors, but also maybe what might be causing high species richness in the plant community.
All right. Shift to the view. Hot there, huh?
It is hot. I close my windows because if I don't, the Amtrak train will just blow me out of here for a minute.
boy. All right, so we've got some new questions here. It might be a typo, but what's the next star for the quarry, for the Quarry Pond Marsh? What's the next stage?
So
the next stage. There we go.
Yes. So I think the next stage is, I know Dave Burke and I have already had these conversations a little bit. It'd be really cool to see if wetland soils have actually developed out there or not, especially now it's been 35 years. And I really hope someone, when I'm in my mid-career or something, will come back and do the same thing again, maybe looking at it after 40 or 50 years. I'm really curious to see if this system actually truly becomes a scrub shrub swamp of some kind, or if really this herbaceous material really persists. Yeah.
Great. I'm just going to add a side note that, I think Grant did a nice history of what was going on with Quarry Pond, but I just have to say on a personal note, I have been saying for 10 years, running field trips, maybe longer, to that site, oh, we really need to redo this study. And when Grant heard me say that and said, yeah, that'd be great, and actually went out and did it, it was like, it was such an important fulfillment of this sort of like hanging idea that would just be such an exciting thing to do, and just ran with it, and did far more than I even would have thought to do. So on a personal note, I'm really proud of you on that. Okay, I won't embarrass you any further. It looks like there's some more questions in here. I see how fast, this is from Connie, how fast are wetlands disappearing across the country, or are they stabilizing?
Yeah, that's a good question. Normally the federal government conducts a federal wetland inventory every 5 years, but the last one that was published was back in 2009. So it's been 11 years, and I don't really know why they haven't conducted one, or if they just do now just regular mapping without doing a big report on this. Back from 2004 to 2009, really the wetlands in the country had roughly stabilized. We lost a little bit. And I think most of the causes for those were external, so not human man-made. So salt marshes getting wiped away from sea level rise, persistent drought out in the west can be a contributing factor. So it looks like it's roughly stabilizing. And now the question is, can we start restoring them in meaningful ways?
Excellent. Okay, we got more questions coming in. This is from Lars. Great job, Grant. You mentioned your living shorelines had recovered about 50%. Do you expect them to return to 90 to 100% in X many years?
Yeah, that's a good question. Marino Mateus et al. 2012, which I showed, is not encouraging. It looks like it reaches maybe 70 or 80%. What my best guess is that eventually vegetation and minnows will reach really similar levels, but it might require 50 to 100 years for those salt marsh soils to really take place, or to really recover properly. And that's just a natural thing of wetland soils. They just take a long time, especially when we've almost kind of slightly handicapped them with giving them a bunch of sand that drains really easily. So I think for the meaningful things of fish and veg, which we can easily see, I think it's sooner than later, but soils, it's much later. Yeah, that's a good question.
Okay, looks like we've got a little more coming in here. Oh, here we go. This one is from David Burnett. Do you think a beaver family could lead to a dynamic that lasts forever at a site like this? Oh boy, you walked into it, huh?
Sounds like someone read my thesis. So if I had time, I actually discussed some of the mechanisms that might explain why we see the patterns we see, and I just didn't have time. But one of them I hypothesized was beavers have been at the site since roughly after right after it was created. And they actually documented that the water level went up about 2 to 3 feet that was originally designed. And I'm guessing that it flooded areas enough to create this sedge meadow marsh, the red maple swamp, and the scrub shrub marsh. They're also maintaining channels, and they're allowing more water to flow throughout the areas, which I think is why some uplands ended up changing into wetland over time.
Okay, great. We've got one from Laura Day. And I like the direction of this one. Do most of the funds for protection and restoration of wetlands come from government legislation, or are they privately funded by grants?
Yes. from what I've just kind of read a little bit, a lot of it is government or requirements under regulations. However, there is a lot of big money when it comes to restoration. A joke in ecology, and I'll say it out loud, is bird people have a ton of money. And I know Audubon and Ducks Unlimited have plowed a ton of money into prairie pothole systems out in the Midwest. So it's a combination of both, so yes.
Great question. All right, well, it looks like the Q&A is winding down. There's a few more here. I'll let you field that one directly or enjoy that one directly. It's awfully hot. I think we've taken the time that we need, unless there are some hot burning final questions. I think we will adjourn this portion of the defense process with the public.
Cool.
Congratulations on a fine presentation. The feedback you're getting here, I hope you're going to be saving the chat, because you're going to need a bigger hat. And we are now going to close the session. For the public who's watching, we're going to take a little break, and then Grant is going to defend with his committee privately at Jackson Estuarine Laboratory. And with any luck, he'll pop out the other side and can reach out to all and let you know how it went. All right, so once again, thank you all for being here. Congratulations on a fine presentation, Grant, and we will see you in about an hour.
Awesome, thanks everybody, I really appreciate it.
Yay, good job, Grant, congratulations.
Congrats, Grant, good job.
Yay.
Good job, Grant. Love you, buddy. Good job.
Good job, Grant.
Good job, Grant, for Mom and Dad.
We love you.
Way to go, Grant, from your dearest aunt.
Say hi, Grant. Say hi. Hi, say hi, Grant.
Nice job, Grant.
Thanks, Heather. Cool. We can probably end it now. That sounds good.
Yeah.
All right, I'm going to sign out.